Yes, thanks a lot for this initiative, and in particular, I think that the need of reproducibility and benchmarking is probably currently what one of the main factors holding back the spread of single pixel imaging. So I think this is really great to have this kind of event. So my name is Nicolas Ducros, and I'm an associate professor at Creatis in Lyon. My main research interests include image reconstruction for in the field of biomedical imaging, and I've been working in the field of single pixel imaging since 2015 now, first in collaboration with Polytechnico Milan, and I am now currently leading two different projects in Lyon on single pixel imaging, one for fluorescence neurosurgery and the other one for the fluorescence imaging of animal models. So the presentation will be about SPyRiT, which is our open software dedicated to image reconstruction for single pixel imaging, but the presentation will be broader than the title suggests, because I will also describe Openspyrit, which is actually a full ecosystem for open research in single pixel imaging, and it also includes an open software for image acquisition and also some data sets. So first, I'd like to start with reminder of the acquisition principle of single pixel imaging. So this is a basic setup here. So we have the sample here. Here we have a transparent sample, which is illuminated from behind using an LED lamp, but we could also use image and reflection. Here we have a digital macro mirror device, which is an array of tiny micro mirrors that can reflect light into two different directions. For instance, here, when we upload this pattern onto the DMD, the white pixel will reflect light towards here a spectrometer, while the dark pixel will reflect light in this direction. So the principle is to upload a pattern onto the DMD, measure a spectrum, then upload another pattern onto the DMD, measure another spectrum, and so on and so forth. And this is how we collect the data. Then, from the set of spectra measured on the spectrometer using different patterns, we need a reconstruction algorithm, because obviously what we see in one particular spectrum is the combination of all the spectrums coming from the scene for the white pixels that corresponds to the pattern that was uploaded onto the DMD. So we need this reconstruction algorithm to recover our hypercube. So we have this three-dimensional cube, x, y being the spatial coordinates, and lambda being the spectral coordinate. And for instance, here we directly image our LED lamp, and this is what we get. So we get a bunch of images, XY images at different wavelengths. Okay. So now I'm gonna introduce the Openspyrit ecosystem. In 2023, so at the beginning of the year, so we introduced Openspyrit. So this is an open access, open source ecosystem for reproducible research in hyperspectral imaging. Openspyrit is composed of, let's say, three main components: SPAS, SPyRiT, and SPIHIM. SPAS is our open software for image acquisition. So we use it mainly to control the DMD, upload the different light patterns onto the DMD, and also to control the spectrometer, acquire the different spectra spectra that correspond to each pattern, and ensure that the acquisition is duly synchronized. The second component is SPyRiT. So this is our package for image reconstruction. I will describe this package later, but this package is, let's say, based on modern approaches for image reconstruction that are based on deep learning. And the last component is SPIHIM, which is a collection of hypercubes that were collected with our single pixel hyperspectral imaging device. I'm going to start with SPAS, which is our single pixel acquisition software. So this software, it's a Python package. The source code is available on GitHub. It can be installed easily. So what you just need is to clone the repository and install it using the pip package manager. Yes. Right now it's working only on Windows, but this is because we are controlling a DMD for which we only have DLLs available for Windows, but it's quite general. This package has been documented, so we use Sphinx, and the documentation is hosted and handled through read the docs. Okay. This is our implementation. So this is basically your hardware device. As I said before, this hardware device is controlled using this this package. So currently it was tested for our DLP 7 spatial light modulator and our Avantes spectrometer. So DMD is DLP 7000 and spectrometer is an Avantes. And we're using the trigger from the DMD to synchronize the acquisition of the different spectra. The second component is SPIHIM. So SPIHIM is our single pixel hyperspectral image collection. This collection is FAIR. So if you don't know FAIR, FAIR data is our data which meets the principle of findability, accessibility, interoperability, and reusability. The acronym and principle was defined in 2016 by a consortium of scientists in order to have data that could be used over the time, and this is not so easy to make a database fair, but I think it makes a difference then, because it really ensures that this can be used over the years. So the data, the SPIHIM collection gathers raw data acquired from our system. So basically raw spectra. So for each sample that we image, we make available the raw data. We also make available some metadata that includes the type of the source, the version of the software, type of version of the DMD, version of the spectrometer, integration time, and so on and so forth. So we have a lot of metadata, which also proved very useful when you want to exploit some data sets like some months after their acquisition. And we also upload the hypercubes that we reconstructed using two different techniques, like let's say, a standard reconstruction approach where you just compute the pseudo-inverse solution of the inverse problem, and also the hypercube obtained using our deep reconstruction methods. So currently we have more than 200 hypercubes that are in open access. If you want to have an overview of the collection, I think a good start is to have a look at the supplementary material that was published together with the paper. So if you just Google Openspyrit, it was published in Open Optics Express. You will find the paper and the supplementary material. Okay, so it looks like this. So I hope that you see now a PDF file, which is the supplementary material. So here, just as an illustration, that was an image that was obtained by imaging the Thorlab box. So you may recognize here the dog. So here we display four different spectral channel. So we have many different samples. So that was just a tree leaf here, color checker, and so on and so forth. So we have many of them. Okay, and there is also a list here at the beginning where we list all the different samples that were imaged using our system. We've here an overview of an RGB overview of the sample, which looks orange here just because our spectral photometer is actually was chosen to image between 500 and 750 nanometers. Okay. If you want to see and have access to the full collection, it's very easy. So you just have to go to our so-called pilot warehouse. So this is completely open. So you will see this page, which is fully open. So here you can see some private folders, but what you're interested in is the data and soft folders. So for instance, you click on data. Here we have different versions of the setup. So we can choose one, let's say this one, and Thorlabs box was there. So if you click Thorlabs, you have two different kind of acquisition with two different kind of length here. Everything is described in the folder. And what you could get here is the Hadamard reconstruction. So this is the hypercube. You have the metadata, you have the reconstruction using the NN neural network, and here you have the raw data, and there's also an overview folder in which you can take a look at the image that was reconstructed. So for instance, this is the image that was reconstructed using the Hadamard standard reconstruction, and this one is going to be the same using the neural network. So there's a lot of data. Probably you have to go there and have a look at what you need. Okay. This is it for the SPIHIM collection, and now I'm gonna talk about SPyRiT, which is our single pixel reconstruction toolkit. So here I displayed first some results. In the top row, you have 3 different samples that were imaged and reconstructed using what I call naive reconstruction, which is, let's say, the standard reconstruction. I will tell a bit more later about the standard reconstruction. And here on the bottom row, we have the reconstructions obtained from the same data using a deep reconstruction network. So you can see an improvement of the image quality, reduction of the noise, and this is something you could evaluate more precisely in simulated data and also in experimental data. So okay, so how to get the bottom line of the previous slide? So first of all, I'd like to maybe formalize a little bit the problem. So what we have to solve is a linear inverse problem. M lambda equals hf lambda plus noise. M lambda is the measurement vector. Here, this measurement vector contains all the different measurements that were measured for the different light patterns that were uploaded onto the MD for a specific lambda. So in this vector here, we have like, it's the, let's say, third channels of the first spectrum, second spectrum, third spectrum, and so on and so forth. So this is the way you build your M lambda vector. And this relates to a slice of the hypercube denoted F lambda. So F lambda here is this slice at wavelength lambda of your hypercube. And this equation is verified for all different spectral wavelengths. Okay, what you measure is M lambda. What you know is age, because age contains all the different spatial light patterns that were uploaded onto the DMD. So every row of this age matrix actually is a light pattern. And from that, you want to get access to F lambda. So basically, what you have to do is to solve a linear system of equations that was perturbed by noise. To get the measurements, what you have to do is to acquire a sequence of measurements. So you upload the first pattern, you measure the first spectrum, and then you upload the second pattern, measure the second spectrum, and so on and so forth. So if you want to get fast acquisition, what you have to do is to reduce the number of patterns that you upload onto the DMD. So you end up with a flat linear system like this, where age is a flat matrix, and this accelerates the acquisition. However, this dramatically degrades the image resolution. And this is where you need a good method for reconstructed F from age, from M lambda. So to do so, we started working. I would say like almost 5 years now ago on the data-driven approaches. So data-driven approaches are different from the, let's say, previous generation of methods where you usually solved an optimization problem where you have a data fidelity term and regularization term. So here, what you look for is you look for here a non-linear model. Actually, it's an estimator that takes as an input the measurement, and that outputs f star here, which is close to the hypercube that you are looking for. So you look for this estimator, and you look for this estimator as a non-linear estimator called model in the deep learning terminology. So what you do to get access to this non-linear model is that you take a database. So actually what you need is you need a lot of measurement image pairs. So you need a lot of pairs like this. So you need a hypercube or a slice or an image and the associated measurement. And then you look for the parameters of the nonlinear problem. Parameters are denoted theta here. You look at a set of parameters such that the nonlinear model outputs something which is close to the true image that you're looking for. So you try to minimize the distance between the two here in the least squares sense. To solve this optimization problem, you can benefit from the optimization machinery which is available now in PyTorch or TensorFlow. So yes, this has become quite easy nowadays. Okay, so the next question is how should I choose this nonlinear model, because I am optimizing the parameters of the model, but the models has to be chosen before the training starts. The good answer and a very practical answer is to choose G theta as a neural network. Why? Because it has been shown empirically, and we have a lot of empirical results that shows that if you consider a neural network with many different layers, many different neurons, then what you can achieve is a reconstruction performance that is excellent. In practice, it's always outperformed optimization-based approaches. Here's one of the first architecture that was proposed in literature. It's called AutoMap. It has a lot of parameters, as you can see here. It's very difficult to train, but once it's trained, it has very good performance. Actually, it outperforms all the previous strategies that were proposed in literature. To train such a network, training such a network is time consuming. It typically requires several hours or days or even weeks. But once the network is trained, then the so-called inference, which means the computation of the solution given the measurement vector, is very fast. So typically less than a second. So this is very this is very good also in practice. However, despite the impressive results, deep learning has also raised concerns. The main is probably that this is a black box with no physical or mathematical basis, and I mean, you could not say that this is just a huge black box which is working well, because if you go to the radiologist or the medical doctors, they want to know more about what's going on inside the black box. The same for the physicists. This is why I would like now to introduce an emerging technique, which is called algorithm unrolling, which is also related to a plug and play method. This technique is it provides basically connection between iterative algorithms that are widely used in signal processing and in image reconstruction, and deep neural network. This is why it's interesting. And this technique has attracted a lot of attention in the last few years. Also thanks to its potential in developing high performance but interpretable neural network architectures from training sets with let's say reasonable size. So how does it work? Basically, you start with an iterative algorithm, standard algorithm such as this one. So in this algorithm, which is iterative, you have two steps. The first step is basically, so you may recognize it, it's a gradient descent step. So here, this is basically the gradient of a data fidelity term that would be just L2 norm squared of the residuals. And you have a second step, which can be interpreted as an image domain denoiser, but that could also be interpreted as a projection onto the set of accessible solutions, and this is how you iterate. If you don't know about this projection step, what you could do is that you could just learn it. So basically, you write this algorithm. You say, okay, I don't know about the set of acceptable solution, so I will learn it from the data. And so you just learn this term. And this is just a diagram that shows how this two-step iterative algorithm could be implemented. So you have here a neural network that actually implements this first equation, and here you have another neural network that implements the second equation. You iterate over these two neural networks. Usually what you do is that you fix the number of iteration to a small number, typically 5 or 10, and you train it with you train it using an image database, and this is it. Okay, so now I'm gonna come back to the SPyRiT toolbox. So we provide some core component that allows you to implement such algorithms. The core components are the measurement, some measurement operator. It's called core MEAS. We have core noise, which allows you to implement different kind of noise models. We have core recon that allows you to implement different kind of let's say standard reconstruction approaches that are now embedded into deep reconstructions. And we have also another one that allows you to have access to the standard neural networks such as UNet, convolutional layers, and so on and so forth. And this is how it simplifies your life, I would say. So if you want to implement this kind of thing, what you will have basically to do is that you will have to import some measurement operator from SPyRiT. So typically, if you want to consider Adamat pattern that are split into the positive and negative components, you just import AdamSplit. If you want to consider Poisson noise, you just import Poisson from SPyRiT.core.noise. Then you instantiate your AdamSplit, saying, okay, I'm going to consider, let's say here, 512 measurements, and I'd like to recover a 128 by 128 image. And you define your Poisson noise. Here 100 means that you expect at maximum 100 photons in some pixel, and this is it. You have a way to implement your data simulation. The same applies to the reconstruction modules. This is going to be my last my last slide. Just want to say that we've implemented we've added to the documentation some tutorials. So if you want to know more, you can have a look at the tutorials. It's available through GitHub in the documentation, and this is it.